In late 1995, an astronomer named Robert Williams decided to do something strange. He was the director of the Space Telescope Science Institute. He had discretionary time on the Hubble Space Telescope. Most astronomers used their time to point Hubble at something they knew was there. A nebula, a star cluster, a specific galaxy. Williams wanted to point it at nothing. He chose a patch of sky in the constellation Ursa Major. It was a spot famously empty. It was tiny, about the size of a grain of sand held at arm's length. His colleagues thought it was a waste of precious telescope time. Some were openly hostile about it. But he went ahead. For 10 consecutive days, from December 18th to December 28th, Hubble stared at that dark, empty patch. It took 342 separate exposures. When the images were processed and combined, the result was staggering. The picture was not empty. It was filled with light. There were over 3,000 distinct objects in that tiny speck of darkness. Almost every single one was a galaxy. Some were young and chaotic. Others were old and well-formed. They were billions of light years away. The image, called the Hubble Deep Field, did more than just show us some new galaxies. It fundamentally changed our sense of scale. The universe wasn't just big, it was incomprehensibly full. Our old ideas, even the ones from just a few decades earlier, were shown to be timid, small, and utterly wrong. It was a powerful reminder our quest to understand the cosmos is a history of brilliant ideas that explained everything perfectly, right up until the moment a new piece of evidence showed they were completely wrong. Number 19, the Earth sits still at the center of everything. The sun rises every day in the east and sets in the west. The moon does the same. The stars wheel overhead in a predictable nightly procession. For over 2 millennia, the most obvious explanation for this was also the accepted scientific truth. The Earth was stationary, and everything in the heavens revolved around it. This wasn't just a lazy assumption. It was a sophisticated system developed by some of history's greatest minds. The Greek astronomer Claudius Ptolemy, working in Alexandria, Egypt, around 150 AD, gave this model its ultimate form. His book, The Almagest, was the definitive astronomical textbook for the next 1,400 years. It was so successful that some of its star catalogs were still being used on ships into the 17th century. The model wasn't just a simple diagram, it was a predictive mathematical machine. The core idea was simple. Earth was a sphere at the center. Around it, in perfect circles, moved the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Beyond them was a sphere of fixed stars. This was built upon the physics of Aristotle, who had argued a century earlier that the Earth had to be the center. His reasoning was based on the nature of the elements. Earthly things, made of earth and water, naturally fell towards the center of the universe. Heavenly things, made of a fifth perfect element called aether, naturally moved in perfect circles. It was an elegant, complete system that explained both why rocks fall and why stars move. It felt right, but there was a problem. The planets didn't move in perfect, simple circles. Sometimes they appeared to slow down, stop, and even move backward in the sky for a few weeks before continuing on their way. This is called retrograde motion. A simple geocentric model couldn't account for this. This is where the genius of Ptolemy came in. To save the central Earth model, he introduced 2 clever devices. The first was the epicycle. A planet didn't orbit the Earth directly. Instead, it moved in a small circle, the epicycle. And the center of that small circle moved along a larger circle around the Earth, the deferent. By adjusting the sizes and speeds of the epicycle and the deferent, Ptolemy could make a planet appear to move backward. It was a brilliant mathematical fix, but even that wasn't enough to match the precise observations. So he added another tool, the equant. He proposed that the center of the deferent, the large circle, didn't move at a constant speed around the Earth. Instead, it moved at a constant speed as seen from another point, offset from the center, called the equant point. This broke the rule of perfect, uniform circular motion, a major concession, but it worked. The system of epicycles, deferents, and equants was incredibly complicated. It was a messy contraption of wheels within wheels, but It predicted the positions of the planets with remarkable accuracy for its time. 4 centuries, if you wanted to know where Mars would be on a given night, you used Ptolemy's system. It was a testament to human ingenuity. It took a simple, wrong idea and through sheer brain power, patched it and tweaked it until it matched reality. The model's ultimate downfall came not because it was inaccurate, but because a much simpler explanation emerged. The heliocentric model with the sun at the center explained retrograde motion naturally. As the faster moving Earth overtakes a slower moving outer planet like Mars, Mars appears to go backward against the background stars like a car you pass on the highway. No epicycles needed, but it took until the work of Copernicus, Kepler, and Galileo in the 16th and 17th centuries to finally dislodge the 1,400-year-old idea that we were the unmoving center of it all. Number 18, the universe is made of solid, invisible spheres. Before the concept of gravity, the motion of the planets was a deep mystery. Why did they stay in their orbits? What held them up? The ancient Greeks, particularly Aristotle, provided an answer that was both physically intuitive and deeply poetic. You know, they believed the heavens were a series of nested, solid, crystalline spheres. You know, these spheres were transparent, made of the perfect fifth element, the aether. Embedded in each sphere was a celestial body, the moon in the first, the sun in another, each planet in its own sphere, and all the stars fixed to the final outermost sphere. These spheres were real, physical objects. They were interlocked and rotated at different speeds, carrying the celestial bodies along with them. This explained why the planets moved across the sky. It wasn't the planets flying through empty space. It was their entire sphere turning. This model solved a lot of problems. It provided a physical mechanism for celestial motion. It explained why the stars all moved together as one, a fixed pattern in the sky. And it created a finite, enclosed, and orderly cosmos, which was a comforting thought. This idea persisted for nearly 2,000 years, evolving in complexity. Medieval Islamic and European scholars debated the number of spheres and the mechanics of their rotation. Some proposed that the spheres rubbed against each other, creating a divine sound, the musica universalis, or harmony of the spheres. This was an idea first put forth by the Pythagoreans centuries earlier. They believed the mathematical ratios between the orbits were the same as the ratios that create musical harmony. The cosmos was, in a very literal sense, a symphony. This vision of a clockwork universe made of real, tangible gears and spheres was the dominant cosmological model for longer than any other in human history. The first major crack in this solid model came in 1577. A great comet appeared in the skies. A Danish astronomer, Tycho Brahe, made meticulous observations of it. Using parallax, the same principle your brain uses to perceive depth, he tried to measure its distance. He had observers at different locations measure the comet's position against the background stars at the same time. If the comet were close, in the Earth's atmosphere or in the sphere of the moon, its position should have shifted noticeably from different vantage points. Tycho found no discernible parallax. His calculations showed the comet had to be far beyond the moon. It was moving through the region where the solid, crystalline spheres of the planets were supposed to be. A comet could not pass through a solid sphere. Therefore, the spheres did not exist. The heavens had to be empty, or at least filled with a fluid substance. This was a revolutionary conclusion. It shattered the physical basis of the cosmos that had been accepted since Aristotle. It meant the planets were not being carried, they were moving on their own through a vast empty void. This raised a new, terrifying question. If they weren't attached to spheres, what kept them from falling? What guided their paths? Tycho's observation of the 1577 comet was a critical blow to the old cosmology. It cleared the way for a new understanding of the heavens, one that would require a new physics. It would be Isaac Newton, a century later, who would provide the answer with his theory of universal gravitation, a mysterious force acting at a distance across the very emptiness that Tycho's comet had revealed. The beautiful, solid, musical cosmos was replaced by a cold, empty space governed by an invisible force. Number 17, the universe is a machine made of swirling vortices. After Tycho Brahe showed the heavens were not made of solid spheres, and before Isaac Newton explained them with gravity, there was a period of intense confusion. If the planets were just floating in empty space, what pushed them along in their orbits? The French philosopher and mathematician René Descartes offered a compelling mechanical answer in the mid-17th century. He was deeply uncomfortable with the idea of action at a distance, like some kind of magical occult force reaching across the void. He believed everything in the universe had to be explained by matter in motion, by things physically touching and pushing each other. His theory, known as the Cartesian vortex theory, was a purely mechanical cosmology. Descartes proposed that the entire universe was filled with a substance, a sort of invisible fluid or aether. There was no such thing as a true vacuum. This fluid was constantly in motion. The sun, he argued, rotated on its axis, and in doing so it stirred the surrounding fluid into a giant whirlpool or vortex. This solar vortex filled the entire solar system. The planets were caught in this swirling vortex like leaves in an eddy in a stream. They were swept around the sun not by a mysterious pull, but by the physical current of the ethereal fluid. It was a brilliant, intuitive idea. It explained planetary orbits using simple, everyday mechanics. There was no spooky action at a distance. It was all just pushing and shoving. The theory also explained the orbits of moons. Jupiter, for example, was itself a smaller, spinning object that created its own little vortex, trapping its moons and sweeping them around with it. The entire cosmos was a nested system of these swirling vortices of varying sizes. The vortex theory was hugely influential. For a time, it was the leading scientific explanation for the cosmos, especially in continental Europe. It was a complete philosophical system that seemed to banish mysticism from the heavens. It explained not just the orbits, but also the formation of the solar system. The vortex, over time, would naturally sort matter by density, with heavier stuff clumping together to form planets. It even tried to explain gravity itself. According to Descartes, the swirling particles of the vortex tended to fly outward, creating a pressure that pushed objects on Earth downward. Gravity wasn't a pull from the Earth, it was a push from the heavens, but the theory had major problems. When Isaac Newton published his Principia Mathematica in 1687, he not only laid out his own theory of universal gravitation, but he also systematically dismantled Descartes' vortex model. And Newton showed, with rigorous mathematics, that a vortex could not possibly produce the observed orbits of the planets. Kepler's laws, derived from observation, stated that planets move in ellipses, not circles, and that they speed up when they are closer to the sun. A simple fluid vortex would create circular orbits with speeds that decrease closer to the center, the exact opposite of what is observed. Newton also demonstrated that a vortex dense enough to push the planets along would create so much drag that the planets would have spiraled into the sun long ago. Newton's theory of gravity was mathematically precise, and its predictions matched observations perfectly. It didn't explain why gravity worked, which bothered Newton himself, but it described how it worked with incredible accuracy. Descartes' beautiful, mechanical, intuitive model was crushed by Newton's ugly, counterintuitive, but undeniably correct mathematics. The universe, it seemed, was not a simple machine. It operated on rules that were far stranger than clockwork. Number 16, the Earth is expanding like a balloon. The continents look like they fit together. The bulge of South America tucks neatly into the coast of Africa. This observation is old. But what could cause continents to drift apart? In the 20th century, before the theory of plate tectonics became widely accepted, a number of alternative ideas were proposed. One of the most radical and surprisingly persistent was the expanding Earth theory. Proponents of this idea argued that the continents weren't drifting across a static globe. Instead, the entire Earth was getting bigger. The continents were once a single shell of crust covering a much smaller planet. As the Earth expanded, this crust cracked and rifted apart, and the growing gaps between the pieces became the ocean basins. This theory had a certain visual appeal. If you imagine, shrinking the Earth and removing the oceans, the continents do fit together into a solid shell with very few gaps. The idea was first seriously proposed in the late 19th century, but gained its most famous advocate in the 1950s and 60s, an Australian geologist named S. Warren Carey. Carey was a respected geologist who initially supported continental drift, but became frustrated with its inability to explain certain large-scale features of the seafloor. He argued that features like the mid-ocean ridges were not places where new crust was being created and pushed aside, but were instead giant cracks opening up as the planet's interior expanded. The expansion, he and others argued, was caused by some unknown process in the Earth's core. Some suggested a decrease in the universal gravitational constant, which would allow matter to decompress. Others proposed exotic phase changes or matter creation within the core. The expanding Earth theory seemed to solve several problems at once. It explained the jigsaw puzzle fit of the continents, it explained why the ocean floor is geologically much younger than the continents, it simply hadn't existed on the smaller, earlier Earth. It also offered an explanation for the reduction in shallow seas over geological time. On a smaller Earth, a given amount of water would create vast, shallow oceans matching the fossil record of certain periods. For a while, it was a serious contender. It was a grand, unifying idea that tried to explain the Earth's entire geological history with a single, simple mechanism growth. The theory was ultimately proven wrong by a mountain of evidence that supported plate tectonics. The first key piece was paleomagnetism. When volcanic rocks cool, magnetic minerals within them align with the Earth's magnetic field at that time, like tiny compass needles frozen in place. Scientists studying these ancient magnetic fields found that rocks on different continents pointed to different north poles. But if you moved the continents back together, as in the continental drift model, the poles aligned. This was strong evidence that the continents had moved relative to each other. The expanding Earth model couldn't easily account for this. The decisive blow, however, came from precise geodetic measurements. Using satellites, GPS, and very long baseline interferometry, scientists could directly measure the movement of the continents and the size of the Earth. These measurements confirmed that continents are moving at rates of a few centimeters per year, and crucially, that the Earth's radius is not changing. The planet is not expanding. The theory of plate tectonics, with its mechanisms of seafloor spreading at mid-ocean ridges and subduction at trenches, where one plate slides under another, provided a complete and evidence-backed model that explained everything the expanding Earth theory tried to, and more. It was a beautiful, simple idea, but the planet itself told us it was wrong. Number 15. The sun is a burning ball of coal. For most of the 19th century, one of the biggest questions in cosmology was the age of the sun. It was clearly the engine of the solar system, the source of the light and heat that made life on Earth possible. But what was its fuel, and how long could it last? The best scientific minds of the era tackled this problem. The most famous and influential answer came from the preeminent physicist of the day, Lord Kelvin. In the 1860s, Kelvin, a master of thermodynamics, calculated the sun's age based on the best physics he knew. He dismissed the idea that the sun was powered by chemical burning, like a giant lump of coal. He correctly calculated that a sun made of coal would burn out in just a few thousand years, which was clearly contradicted by geological evidence. Instead, Kelvin proposed that the sun's heat was generated by gravitational contraction. He reasoned that the sun was a slowly collapsing cloud of gas. As the gas particles fell inward under their own gravity, their potential energy would be converted into kinetic energy, or heat. This mechanism, now known as the Kelvin-Helmholtz mechanism, is a real process and is thought to be how protostars generate heat before they are hot enough for nuclear fusion to begin. Kelvin's calculations were meticulous, based on the sun's mass and its current rate of energy output, he concluded that the sun could be no more than 20 to 40 million years old. Any older, and it would have already collapsed completely. He also calculated a similar age for the Earth based on how long it would take a molten sphere of rock to cool to its current temperature. This was a genius application of the most advanced physics of the time. It was a quantitative, evidence-based argument that seemed unassailable. And it was a disaster for other fields of science. Charles Darwin had recently published his theory of evolution by natural selection. Darwin's theory required vast amounts of time, hundreds of millions, or even billions of years, for the slow process of natural selection to produce the diversity of life we see today. Geologists like Charles Lyell also argued for a very old Earth based on the slow rates of sedimentation and erosion. Lord Kelvin's 20 million year age limit created a major scientific crisis. It seemed to put an absolute physics-based ceiling on the age of the Earth and the Sun, which directly contradicted the needs of biologists and geologists. For decades, it was a standoff. Many scientists assumed the geologists and biologists must be wrong because Kelvin's physics was so solid. How could you argue with the laws of thermodynamics? The solution came from a completely new area of physics, one that Kelvin could not possibly have known about nuclear physics. In the early 20th century, with the discovery of radioactivity and Einstein's famous equation, E equals mc squared, scientists began to understand that vast amounts of energy could be released from the atom itself. In the 1920s and 30s, physicists like Arthur Eddington and Hans Bethe figured out the true power source of the sun, nuclear fusion. In the sun's core, under immense temperature and pressure, hydrogen atoms are fused together to create helium. In this process, a tiny amount of mass is converted directly into a huge amount of energy. This process is vastly more efficient than gravitational contraction. It could keep the sun shining not for millions, but for billions of years. We now know the sun is about 4.6 billion years old and has enough fuel for another 5 billion years. Kelvin's logic was flawless. His physics was impeccable, but his assumptions were wrong. He was working from an incomplete picture of the universe. The sun wasn't just a cooling ember or a collapsing gas cloud. It was a nuclear furnace powered by a force that had not yet been discovered. Number 14, the redshift of galaxies is caused by tired light. In the 1920s, Edwin Hubble made a landmark discovery. He observed that the light from distant galaxies was shifted towards the red end of the spectrum. This is known as redshift. Furthermore, he found a direct relationship: the farther away a galaxy was, the greater its redshift. The most straightforward interpretation of this was the Doppler effect. If a galaxy is moving away from us, the light waves it emits get stretched out, increasing their wavelength and shifting them towards red. Hubble's observation meant that almost all galaxies are moving away from us, and the farthest ones are moving the fastest. This was the first evidence for the expansion of the universe. It is the cornerstone of modern cosmology and the Big Bang theory. But not everyone was convinced. The idea of a dynamic, expanding universe was a radical departure from the prevailing view of a static cosmos. Some scientists looked for an alternative explanation for the redshift. In 1929, the same year as Hubble's discovery, the Swiss astronomer Fritz Zwicky proposed one. He suggested the tired light hypothesis. Zwicky was a brilliant but famously eccentric astronomer who also first proposed the existence of dark matter. His tired light idea was that photons of light simply lost energy as they traveled over the vast cosmic distances. This loss of energy would correspond to an increase in wavelength, causing a redshift without any need for the universe to be expanding. The light wasn't redshifted because the source was moving away. It was redshifted because it got tired on its long journey. This was an appealing idea for several reasons. It preserved the idea of a static, infinite universe, which many scientists, including Einstein at first, found more philosophically palatable. It explained the redshift-distance relationship neatly. The farther the light had to travel, the more energy it would lose, and the greater its redshift would be. It was a simple, conservative alternative to the mind-bending concept of expanding space. For several decades, tired light remained a fringe but plausible competitor to the expanding universe model. Opponents would periodically suggest mechanisms for how the light might lose energy, such as interactions with intervening matter or some unknown property of photons themselves. The hypothesis was eventually ruled out by a series of observations it couldn't explain. One of the most clever tests involves the surface brightness of galaxies. In a static universe, a galaxy's apparent brightness would decrease with distance, but its surface brightness, the brightness per unit area, should remain constant. In an expanding universe, however, the surface brightness should decrease dramatically with distance because the light is stretched out over a larger area. Observations have confirmed the prediction of the expanding universe model. The surface brightness of distant galaxies is much lower than predicted by any tired light model. Another key piece of evidence is time dilation in distant supernovae. The light curves of distant Type Ia supernovae, their process of brightening and fading, are observed to be stretched out over a longer period of time than nearby ones. This is exactly what you would expect in an expanding universe where time itself is stretched along with space. A tired light model where photons just lose energy has no mechanism to explain this stretching of time. The final nail in the coffin was the perfect black body spectrum of the cosmic microwave background radiation. An expanding universe naturally produces this spectrum, but tired light models struggle to explain it without looking incredibly contrived. The evidence is now overwhelming. The light isn't tired, the universe is expanding. Number 13, the Milky Way is the entire universe. For centuries, astronomers noticed faint, fuzzy patches of light in the night sky. They called them nebula, from the Latin word for cloud. Some, like the Orion Nebula, were resolved by better telescopes into glowing clouds of gas and new stars within our own galaxy. But others, like the one in the constellation Andromeda, remained stubbornly fuzzy. What were they? For a long time, the prevailing theory was that these spiral nebulae were simply gas clouds and star systems in the process of formation, all located within our own Milky Way galaxy. The Milky Way, in this view, was the entire universe. It was a vast, disc-shaped island universe containing every star and nebula that existed. The idea that there could be other similar galaxies, other island universes, was a minority view. It was difficult to prove because there was no reliable way to measure the distance to these faint objects. This debate came to a head in a famous public event in 1920 known as the Great Debate. It was held at the Smithsonian Museum of Natural History in Washington, D.C. Two prominent astronomers argued their opposing views. Harlow Shapley, a well-respected astronomer, argued for the single galaxy model. He had recently made a new larger measurement of the size of the Milky Way, placing the sun not at the center, but far out in the galactic suburbs. His measurements, while a huge step forward in understanding our own galaxy, made the Milky Way seem so enormous that it was hard to believe other similar structures could exist. He argued that the spiral nebulae were relatively small, nearby objects. On the other side was Heber Curtis, who argued that the spiral nebulae were in fact other galaxies located at immense distances far outside the Milky Way. He pointed to the fact that these nebulae seemed to contain vast numbers of stars, and that some of them had nova explosions that, if the nebulae were nearby, would have to be impossibly bright. The debate was not definitively settled at the time. Both sides had good points and weak points. Shapley was actually more correct about the size of the Milky Way, while Curtis was more correct about the nature of the nebulae. The decisive evidence came a few years later, in 1923 and 1924, thanks to the work of Edwin Hubble at the Mount Wilson Observatory in California. Using the new 100-inch Hooker telescope, the most powerful in the world, Hubble was able to resolve individual stars in the Andromeda Nebula. This was a major achievement in itself, but he then identified a specific type of star called a Cepheid variable. These stars have a unique property discovered by Henrietta Leavitt a decade earlier their pulsation period is directly related to their intrinsic brightness. By measuring how fast a Cepheid pulsates, you can know exactly how bright it truly is. By comparing its true brightness to its apparent brightness in the sky, you can calculate its distance with great accuracy. And Hubble found a Cepheid variable in Andromeda and calculated its distance. The result was stunning. He found that Andromeda was nearly 1 million light-years away. Later measurements would revise this to over 2 million light-years. Shapley's own measurements had shown the entire Milky Way to be perhaps 300,000 light-years across. Andromeda was clearly, unambiguously located far outside our own galaxy. It was its own island universe, comparable in size and scale to the Milky Way. The spiral nebulae were not clouds within our galaxy, they were galaxies in their own right. In a single stroke, Hubble's observation expanded the known universe by a staggering amount. The universe wasn't just one galaxy. It was hundreds of billions of them. The idea that our Milky Way was the entire cosmos, a dominant theory for centuries, was completely and totally wrong. Number 12, space is filled with an invisible ether. Light is a wave. In the 19th century, this was a well-established fact thanks to the work of scientists like Thomas Young and Augustin Jean Fresnel. But all waves that we know of travel through a medium. Sound waves travel through air or water. The ocean waves travel through water. So, what was the medium for light waves? Light could clearly travel through the vacuum of space from the sun and stars to the Earth. This posed a major puzzle. To solve it, scientists proposed the existence of a substance called the luminiferous aether. The aether was thought to be an invisible, massless, frictionless substance that filled all of space. It was the medium through which light waves propagated. It was supposed to be completely stationary, a fixed reference frame for the entire universe. The aether was not just a placeholder idea, it was a central part of 19th century physics. Scientists developed elaborate mechanical models of it, trying to explain its properties. It had to be incredibly stiff to support the high speed of light waves, yet it had to be incredibly tenuous to allow planets to move through it without any detectable drag. These were contradictory properties, but the concept was so essential that physicists were willing to accept them. If the aether existed and was stationary, then it should be possible to detect the Earth's motion through it. As the Earth orbits the Sun, it should be moving through this static aether at a considerable speed, about 30 kilometers per second. This motion should create an ether wind. In 1887, two American scientists, Albert Michelson and Edward Morley, set up a brilliant experiment to detect this aether wind. They used a device called an interferometer. It split a beam of light into two perpendicular paths. The two beams traveled the same distance, bounced off mirrors, and were then recombined. If there was an aether wind, the beam traveling into the wind would be slowed down, and the beam traveling perpendicular to the wind would be less affected. When the beams were recombined, this difference in speed should create a specific interference pattern. Michelson and Morley's apparatus was incredibly sensitive, more than capable of detecting the expected effect. They rotated the apparatus, expecting to see a shift in the interference pattern, as one beam turned into the wind and the other turned across it. They found nothing. There was no shift. They repeated the experiment at different times of the day and different times of the year, to account for the Earth's motion in different directions. The result was always the same, a null result. The speed of light was constant, no matter which direction it was traveling relative to the Earth's motion. This was a shocking and profound discovery. It was one of the most famous failed experiments in history. The failure to detect the aether wind meant that the aether, at least as it had been conceived, did not exist. For nearly 2 decades, physics was in a state of crisis. The Michelson-Morley experiment had kicked out one of the fundamental pillars of physics, and no one knew what to replace it with. The resolution came in 1905 with Albert Einstein's theory of special relativity. Einstein took the null result of the Michelson-Morley experiment as a starting point. He proposed 2 postulates first, that the laws of physics are the same for all observers in uniform motion, And second, that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. The second postulate completely eliminated the need for an aether. Light did not need a medium. It was a fundamental property of spacetime itself. The theory of relativity explained why Michelson and Morley got their null result, and in the process revolutionized our understanding of space-time and gravity. The aether, once a central concept in cosmology, was simply abandoned, an elegant and necessary idea that turned out to be completely superfluous. Number 11, the universe is static and eternal. For most of human history, including the era of modern science, the universe was assumed to be, on the whole, unchanging. Stars might die, galaxies might rotate, but the overall stage, the cosmos itself, was eternal and static. It had always existed and would always exist in more or less the same state. This was the view held by Isaac Newton. His theory of gravity, however, presented a problem for this view. If gravity is always attractive, why didn't all the stars in the universe collapse together into one giant clump? Newton's own solution was that the universe must be infinite. In an infinite, uniform distribution of stars, every star would be pulled equally in all directions, creating a state of unstable equilibrium. It was a bit like balancing an infinite number of needles on their points. It was a precarious solution, but it was the best he had. This idea of a static universe persisted until the early 20th century, when Albert Einstein developed his theory of general relativity in 1915. His equations described the relationship between matter, energy, and the curvature of spacetime. When he applied his equations to the entire universe, he found something unsettling. The equations predicted that the universe could not be static. A universe filled with matter would have to be either expanding or contracting under its own gravity. A static universe was not a stable solution. This result bothered Einstein. It contradicted the prevailing wisdom that the universe was eternal and unchanging. He thought there must be a mistake in the equations, or at least that they were incomplete. To fix this problem and force his model to produce a static universe, Einstein introduced a new term into his equations in 1917. He called it the cosmological constant. It was a kind of anti-gravity, a repulsive force inherent in the fabric of space itself that would push things apart. He carefully tuned its value to perfectly balance the attractive pull of gravity, resulting in a universe that was static and stable, just as he believed it should be. It was a mathematical fudge factor, introduced for the sole purpose of making the theory match the philosophical prejudice of the time. A decade later, in 1929, Edwin Hubble's observations showed that the universe was, in fact, not static. It was expanding. The farther galaxies were, the faster they were receding. The evidence was clear. Einstein's original equations had been correct. The universe was dynamic. He had introduced the cosmological constant to prevent a prediction that turned out to be true. He later called the introduction of the cosmological constant the biggest blunder of his life. He abandoned the idea, and for most of the 20th century, the cosmological constant was treated as a historical curiosity, a mistake made by a genius. The story, however, has a surprising twist. In 1998, two separate teams of astronomers studying distant supernovae made a shocking discovery. They found that not only is the universe expanding, but its expansion is accelerating. Something is pushing the universe apart, acting against the pull of gravity. The best explanation for this cosmic acceleration is a mysterious force or energy inherent in space itself, a force that has a repulsive effect. We now call this dark energy, and it is mathematically equivalent to Einstein's abandoned cosmological constant. His biggest blunder may in fact have been his most prescient insight, even if he introduced it for the wrong reason. The original idea of a perfectly static universe was wrong, but the mechanism Einstein invented to create it turned out to be real after all. Number 10, the planets were ripped from the sun by a passing star. How did the planets form? For a long time, the dominant scientific theory was the nebular hypothesis proposed by Immanuel Kant and Pierre-Simon Laplace in the 18th century. It suggested that the sun and planets all condensed from a single large rotating cloud of gas and dust. This model explains many key features of our solar system, like the fact that all planets orbit in the same direction and on roughly the same plane. But in the early 20th century, this theory fell out of favor due to a major perceived flaw related to angular momentum. Being the sun, which has over 99.8% of the solar system's mass, has only about 0.5% of its angular momentum. The rest is in the planets, mostly Jupiter. It was difficult to see how the slow spinning sun could have formed from the same rapidly spinning cloud as the planets. This problem led to the rise of a new class of catastrophic theories. Instead of a peaceful evolutionary process, these theories proposed that the solar system was born in a sudden, violent event. The most popular of these was the Chamberlain-Moulton planetesimal hypothesis, and its later refinement, the tidal theory or close and counter theory, developed by James Jeans. The core idea was that our sun was once a solitary star with no planets. At some point in the distant past, another star passed very close to our sun. The immense gravitational pull of this passing star would have raised a huge tidal bulge on the sun's surface. A long filament of hot gas would have been drawn out from the sun, stretching between the two stars. As the visiting star moved away, this filament of solar material would have been left behind in orbit around our sun. This filament would have been unstable, breaking up and condensing into smaller blobs of gas. These blobs would then cool and solidify to form small bodies called planetesimals, which would then clump together to form the planets we see today. This theory was very attractive for several decades. It elegantly solved the angular momentum problem. The momentum of the planets didn't come from the sun's rotation, but was imparted by the glancing blow of the passing star. It also seemed to explain the distribution of the planets, with the larger gas giants forming from the thicker central part of the filament and the smaller rocky planets at the ends. The theory also had a profound philosophical implication. It meant that planetary systems were incredibly rare. Close stellar encounters are exceptionally unlikely events. If this theory were true, our solar system might be one of only a handful in the entire galaxy. Life in the universe would be an extraordinary fluke. The close encounter theory began to unravel in the 1930s and 40s. The American astronomer Henry Norris Russell showed that it was highly unlikely that the material pulled from the sun would have enough angular momentum to go into a stable orbit so far from the sun. Most of it would either fall back into the sun or be flung off into space. Another fatal blow was delivered by Lyman Spitzer, who calculated that the hot gas ripped from the sun would not condense into planets. The temperature of the solar material would be so high and its internal pressure so great that it would simply dissipate into space like a puff of smoke before it had a chance to cool and clump together. By the mid-20th century, scientists had also resolved the angular momentum problem of the old nebular hypothesis. Hannes Alfvén and Fred Hoyle showed how magnetic fields in the early solar nebula could have transferred angular momentum from the young, rapidly spinning sun to the surrounding protoplanetary disk. With its main objection resolved, the nebular hypothesis was revived and remains the foundation of our modern understanding of planet formation. The idea of a dramatic stellar encounter, while visually compelling, was replaced by the less spectacular but more physically plausible story of slow, patient accretion from a dusty disk. Number 9. Life on Mars built a planet-spanning network of canals. In 1877, the Italian astronomer Giovanni Schiaparelli was observing Mars during a particularly favorable opposition when the planet was close to Earth. Using a new high-quality telescope, he meticulously mapped the planet's surface. He noted a dense network of straight lines crisscrossing the lighter, reddish areas of the planet, connecting the darker regions. He called these features canali, which in Italian simply means channels. It was a neutral, descriptive term. But when his work was translated into English, canali became canals. This single word changed everything. A channel can be a natural formation. A canal is an artificial construction. The idea of Martian canals, and therefore Martian engineers, was born. The idea was taken up and popularized with incredible enthusiasm by an American amateur astronomer named Percival Lowell. Lowell was a wealthy Bostonian who became obsessed with Mars. In 1894, he used his fortune to build a state-of-the-art observatory in Flagstaff, Arizona, specifically for the purpose of studying Mars. For the next 2 decades, Lowell and his assistants produced increasingly detailed maps of Mars, showing a vast and complex network of hundreds of canals. Lowell's drawings depicted a planet covered in a geometric web of perfectly straight lines, some intersecting in oses. He believed these were not just canals, but a planet-wide irrigation system. He theorized that Mars was a dying, drying planet. The advanced Martian civilization had built this colossal network to carry water from the polar ice caps to the equatorial regions to grow crops. This was a grand, romantic vision of an old, wise, and desperate civilization fighting for survival. Lowell wrote several popular books on the subject, which captured the public imagination. For many people at the turn of the 20th century, intelligent life on Mars was not a fringe speculation, it was an established scientific fact. However, even at the height of Lowell's popularity, many professional astronomers were skeptical. When they looked at Mars through their own telescopes, they simply couldn't see the canals that Lowell was mapping. Astronomers like E. E. Barnard, a renowned observer with a powerful telescope, reported seeing only irregular, patchy markings. The debate raged for years. Lowell and his supporters claimed their superior observing sight in the clear Arizona air gave them an advantage. Critics suggested that the canals were an optical illusion. The human eye and brain have a tendency to connect disparate, faint details into straight lines, a form of cognitive bias known as apophenia. The canals were likely just a trick of the eye, a joining of the dots between mountains, craters, and other irregular surface features seen at the very limit of resolution. The final verdict on the canals came with the age of space exploration. In 1965, the Mariner 4 spacecraft flew by Mars and sent back the first close-up pictures of its surface. The images revealed a cratered, moon-like, and disappointingly dead world. There were no canals. No oases, no signs of a dying civilization. Later missions like the Mariner 9 orbiter in 1971 and the Viking landers in 1976 mapped the entire planet in detail. They showed a world of giant volcanoes, a vast canyon system, and dry riverbeds from a watery past, but absolutely no evidence of the geometric network that Lowell had so carefully drawn. Percival Lowell was not a fraud. He was a dedicated and passionate observer who was, in the end, profoundly mistaken. His story is a powerful cautionary tale in science. He saw what he wanted to believe, and his belief was so strong that his own mind created the evidence for him. The Martian canals were not on Mars, they were in the human eye. Number 8. The cosmos follows a fractal hierarchical structure. Is the universe infinite? And if so, how is matter arranged in it? In the 18th and 19th centuries, before the discovery of extragalactic nebulae, this was a major philosophical and scientific problem. If the universe was an infinite sea of uniformly distributed stars, as Newton had suggested, it led to a paradox. Known as Olbers's paradox, it states that in such a universe, every line of sight would eventually end on the surface of a star. The night sky should therefore be as bright as the surface of the sun. Clearly, it is not. The sky is dark. To solve this and other paradoxes, a different model for the structure of the universe was proposed. This was the hierarchical universe, or fractal cosmology. The idea was first suggested by the 18th century scientist Johann Heinrich Lambert, and later developed in the early 20th century by the Swedish astronomer Carl Charlier. They proposed that the universe was not uniform. Instead, it had a nested hierarchical structure, like a set of Russian dolls. Stars were clustered into galaxies. Galaxies were clustered into clusters of galaxies. Clusters of galaxies were clustered into superclusters. The key idea of the hierarchical model was that this pattern continued indefinitely at all scales. There would be clusters of superclusters and clusters of those and so on forever. At each level of the hierarchy, the average density of matter would decrease. As you zoomed out, the universe would become more and more empty. A star is very dense. A galaxy is much less dense on average, as it's mostly empty space. A cluster of galaxies is even less dense. In an infinite hierarchical universe, the average density of the entire cosmos would approach zero. This elegant model solved Olber's paradox. Because the universe becomes progressively emptier at larger scales, most lines of sight would not end on a star. They would pass through the vast voids between the higher level structures, and the sky would remain dark. It also solved the gravitational paradox of an infinite uniform universe. It was a mathematically consistent and philosophically satisfying model of an infinite cosmos. It was also, for a time, supported by observation. As astronomers looked farther out, they did indeed find this clustering pattern stars in galaxies in clusters like our own local group, and those clusters in superclusters like the Virgo supercluster. The model seemed to be on the right track. It looked like the universe was fractal, with the same clumpy, clustered pattern repeating itself on ever larger scales. The downfall of the hierarchical model came in the late 20th century with the advent of large-scale galaxy surveys. Projects like the CFA Redshift Survey in the 1980s, and later, the Sloan Digital Sky Survey began to map the positions of millions of galaxies in 3 dimensions. These maps allowed cosmologists to test the structure of the universe on unprecedented scales. What they found was that the hierarchical fractal structure does not continue indefinitely. The clustering of galaxies exists up to a certain scale, forming vast filaments and walls of galaxies surrounding huge cosmic voids. This is often called the cosmic web, but above a scale of about 300 million light-years, the pattern stops. On the very largest scales, the universe becomes smooth and uniform. The distribution of superclusters is roughly the same everywhere. This observation that the universe is homogeneous and isotropic, the same in all directions on large scales, is now a fundamental tenet of modern cosmology, known as the cosmological principle. The universe is not a Russian doll. It's more like a sponge. It has structure on small scales, but if you zoom out far enough, it all looks the same. The elegant hierarchical model was a brilliant attempt to conceptualize infinity, but the universe turned out to be both simpler and stranger than it proposed. Number 7. The Earth resides on the inside of a hollow sphere. Most cosmological models, right or wrong, place humanity on the outside of a sphere looking in, or on a small ball in a vast expanse. But a bizarre and surprisingly persistent alternative flips this entire concept inside out. This is the hollow Earth theory, which in some of its forms is a complete cosmological model. One of the most detailed concave cosmologies was proposed by an American writer and alchemist named Cyrus Teed in the late 19th century. Teed had a vision in which he claimed the divine truth of the universe was revealed to him. The truth was this: we are not living on the outer surface of a globe, but on the inner surface of a hollow sphere. The entire universe, sun, moon, planets, and stars is contained within this sphere. In Teed's model, which he called cellular cosmogony, the Earth's crust is a 100-mile thick shell. We live on the inside. At the very center of the hollow sphere is the sun. The moon is a reflection of the Earth's surface, and the planets are also mere reflections. The stars are tiny points of light embedded in the shell. Gravity, in this model, is not a pull towards the center of the Earth, but a push from the outside. What we perceive as gravity is actually centrifugal force generated by the rotation of the entire cosmic sphere. Teed's model was a complete, self-contained system that attempted to explain all known astronomical and physical phenomena from this inside-out perspective. He founded a religious commune, the Koreshan Unity, in Florida to promote his ideas. The group even conducted an experiment on the coast of Florida using a long, straight surveying instrument called a rectilineator to prove the concavity of the Earth. Unsurprisingly, they claimed their experiment was a success. This was not just the ramblings of a single eccentric. The idea of a concave, hollow Earth cosmology has been independently proposed several times. In the early 20th century, a German pilot named Peter Bender also championed the idea. He convinced some members of the German military and political establishment that this model was correct. His reasoning was that it would allow them to spy on the British fleet by pointing infrared telescopes straight up into the sky, as the curved surface of the inner Earth would allow them to see across the Atlantic. An expedition was reportedly sent to the island of Rügen in the Baltic to test this, with predictable failure. The hollow Earth cosmology is wrong on almost every conceivable level. It is contradicted by a mountain of evidence. The most basic is the simple fact that we can send rockets and satellites into space. They do not hit a celestial sphere a few thousand miles up. We have photographs of the convex, spherical Earth taken from space. The physics of the model is also nonsensical. A hollow shell of matter does not exert a net gravitational pull on an object inside it, a fact proven by Isaac Newton and known as the shell theorem. And gravity, as we experience, it would not exist. The phases of the moon and Venus, the retrograde motion of planets, the existence of Foucault's pendulum, and the Coriolis effect are all impossible to explain in a concave model, but are perfectly explained by a standard convex rotating Earth. It's a prime example of a theory that is not just wrong, but not even wrong. It's a completely self-contained delusion, a parallel reality physics that starts from a bizarre premise and twists all of reality to fit it. It's a genius work of imagination, but it has absolutely no connection to the real universe. Number 6. The Sun and Moon orbit the Earth, but the planets orbit the Sun. The transition from a geocentric Earth-centered to a heliocentric, Sun-centered model of the universe was not a simple overnight switch. For a time, there was a popular and scientifically robust compromise model that combined features of both. This was the Tychonic system proposed by the great Danish astronomer Tycho Brahe in the late 16th century. Tycho was the greatest observational astronomer of the pre-telescope era. His meticulous, decades-long observations of the stars and planets were far more accurate than any that had come before. He was a giant of empirical science. But he had a major problem with the Copernican, sun-centered model. His objection was based on his own excellent observations. If the Earth were orbiting the Sun, then as we moved from one side of our orbit to the other, we should see a slight shift in the apparent positions of the nearby stars against the more distant background. This is called stellar parallax. It's the same effect you see when you hold your finger up and look at it with one eye, then the other. Your finger appears to shift against the background. Tycho used his best instruments to look for this stellar parallax, and he could not detect it. He concluded, quite logically based on the evidence available to him, that the Earth must be stationary. The stars, he reasoned, would either have to be impossibly far away for their parallax to be unobservable, or the Earth simply did not move. He chose the latter. At the same time, Tycho recognized the mathematical elegance of the Copernican system. It explained retrograde motion and the phases of Venus much more simply than the old Ptolemaic model with its complex epicycles. So Tycho proposed a hybrid model to get the best of both worlds. In the Tychonic system, the Earth was stationary at the center of the universe. The Sun and the Moon orbited the Earth. But all the other planets, Mercury, Venus, Mars, Jupiter, and Saturn, orbited the Sun as it, in turn, moved around the Earth. This was a clever arrangement. It preserved a stationary Earth, which was consistent with the lack of observed stellar parallax and with common sense intuitions. But it also incorporated the main advantages of the Copernican system. The planetary orbits were centered on the Sun, which meant the model was mathematically identical to the Copernican model in terms of predicting planetary positions. A retrograde motion was explained in the same way as the Earth was overtaken by the Sun's entire system of planets. For a time, the Tychonic system was a major competitor to both the old Ptolemaic and the new Copernican models. It was embraced by many, particularly Jesuit astronomers, as a safe, conservative middle ground that avoided the radical theological implications of a moving Earth while still being scientifically up to date. It was a model born from a deep respect for observational evidence. Tycho's inability to detect stellar parallax was a real hard piece of data that his theory had to account for. The model was ultimately proven wrong, but not because its logic was flawed. It was wrong because one of its core premises was based on an observational limitation. The stars are, in fact, impossibly far away. The first successful measurement of stellar parallax was not made until 1838 by Friedrich Bessel, over 250 years after Tycho's death. The parallax shifts are so tiny that they require powerful telescopes and painstaking measurement to detect. Tycho's model was a brilliant, rational, and data-driven attempt to synthesize conflicting information. Well, it was a perfect stepping stone, a genius compromise that was made obsolete only by technology he could never have dreamed of. Number 5, the universe was born from the collision of brains. The Big Bang Theory is incredibly successful, but it has a few nagging problems. One of them is the singularity. The theory predicts that the universe began from an infinitely hot, infinitely dense point. In physics, as we know, it breaks down at a singularity. What came before it? What caused it? These are questions the standard Big Bang model cannot answer. In the early 2000s, a radical new cosmological model emerged from the cutting edge of theoretical physics, specifically from string theory. It was called the ekpyrotic model, or more generally, the cyclic model. It proposed a universe without a singular beginning. The name ekpyrotic comes from an ancient Greek philosophical term for a cosmic conflagration or birth by fire. The model is based on the idea that our three-dimensional universe is a brain short for membrane existing in a higher dimensional space, a bulk. It suggests there is at least one other parallel brain universe existing in this bulk. In the ekpyrotic scenario, the Big Bang was not the beginning of time. Instead, it was the result of a collision between our brain and another brain. Before the collision, the two brains were cold, empty, and parallel. They slowly drifted towards each other in the higher dimension. The collision itself would have been a cataclysmic event, converting the immense kinetic energy of the impact into the matter and radiation that we see in our universe today. This event would look, from our perspective inside our brain, just like a hot Big Bang. The collision would have been nearly, but not perfectly, simultaneous across the brains, and these slight variations would have imprinted the tiny density fluctuations that later grew into galaxies and cosmic structures. This model was genius because it solved several major cosmological puzzles in a new way. It completely avoided the singularity problem. The universe didn't begin from an infinite point, it began from the collision of two large, finite objects. It also offered a natural explanation for the flatness and uniformity of our universe. The brains were assumed to be flat and uniform before they collided, and this smoothness was passed on to our post-Bang universe. The standard Big Bang model explains this with a separate theory called cosmic inflation, a period of hyperfast expansion just after the Bang. The ekpyrotic model didn't need inflation. Furthermore, in its later cyclic versions proposed by Paul Steinhardt and Neil Turok, the collision was not a one-time event. After the collision, the brains would bounce apart, expand, cool down, and slowly become empty again as dark energy spread everything out. Then, a force between the brains would pull them back together, leading to another collision and another Big Bang. The universe would go through an endless cycle of collision, expansion, and contraction. There was no beginning and no end. The ekpyrotic cyclic model was a serious and compelling alternative to inflation. It was mathematically sophisticated and arose from fundamental theories of physics. However, the model has faced significant challenges. One of the biggest problems relates to the predictions it makes about the cosmic microwave background CMB. While both inflation and the cyclic model predict the right kind of density fluctuations, the seeds of galaxies, they predict different signatures in the form of gravitational waves. Standard inflationary models predict that the period of hyperexpansion should have created a background of primordial gravitational waves, which could leave a faint, specific B-mode polarization pattern in the CMB. The simplest periodic models predict that no such gravitational waves would be produced. As our experiments to measure the CMB have become more and more sensitive, they have failed to find this primordial gravitational wave signal, which puts pressure on the simplest inflation models. However, detailed analysis of the CMB data from the Planck satellite has shown features that are a better fit for inflation than for the cyclic model. The debate is not entirely over, and variations of these theories are still being developed. But for now, the standard inflationary Big Bang model remains the consensus, while the beautiful and radical idea of a universe born from a cosmic clap of two parallel worlds remains an unproven, though brilliant alternative. Number 4. Our universe is just one bubble in a cosmic foam. The theory of cosmic inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. This idea elegantly solves several major problems in cosmology, such as why the universe is so flat and uniform. But some versions of the theory lead to a staggering and bizarre conclusion. Our Big Bang was not the only one. This is the theory of eternal inflation, which gives rise to the multiverse. The idea, developed by physicists like Alan Guth and Andre Linde, is that inflation, once it starts, is very difficult to stop completely. It's like a boiling pot of water. Inflation stops in some regions, creating a bubble or pocket universe like ours, where the energy that drove inflation is converted into matter and radiation, leading to a hot Big Bang. But in the vast space between these bubbles, inflation continues. The space between the bubbles expands at an exponential rate, creating more and more room for new bubbles to form. In this scenario, our entire observable universe is just one bubble in an infinite, ever-expanding metaverse or multiverse. Each bubble would have its own Big Bang, its own expansion, and could potentially have its own different laws of physics. The process is eternal. New bubble universes are constantly being created. Our universe is not unique. It is one of an infinite number of universes in a vast cosmic foam. This is a mind-bending concept, but it arises naturally from the mathematics of some of the most successful inflationary models. It's a genius idea because it provides a context for our own existence. It offers a potential explanation for the fine-tuning problem, the fact that the fundamental constants of physics in our universe seem to be perfectly tuned to allow for the existence of stars, planets, and life. If any of these constants were even slightly different, the universe would be sterile. The multiverse offers a simple explanation. There are an infinite number of universes, each with random values for its physical constants. We just happen to find ourselves in one of the rare universes where the constants are right for life to exist because we couldn't exist anywhere else. This is known as the anthropic principle. The eternal inflation multiverse is a powerful and popular idea among many cosmologists. It's the logical extension of the Copernican principle first. Our city wasn't the center of the world, then our planet wasn't the center of the solar system, then our sun wasn't the center of the galaxy, then our galaxy wasn't the center of the universe. The multiverse takes the final step. Our universe isn't even the only universe. It's a profound demotion of our own cosmic significance. So why is this totally wrong? The problem is that, at least for now, it is a completely untestable theory. It is a prediction that comes out of a successful physical model, but the prediction itself seems to be beyond the reach of any conceivable experiment. By definition, the other bubble universes are causally disconnected from ours. The space between them is expanding faster than the speed of light. We can never get a signal from them, we can never visit them, we can never prove they exist. Some physicists have proposed looking for bruises or circular patterns in the cosmic microwave background, which could be the signature of a collision between our bubble and another in the distant past. So far, no such evidence has been found. This puts the multiverse in a strange position. Is it science or is it metaphysics? It's a mathematically derived consequence of a good theory, but if it can never be falsified or confirmed, it falls outside the traditional definition of a scientific hypothesis. It's a grand, compelling, and perhaps even true idea, but until there is a shred of evidence for it, it remains a piece of speculative cosmology. A brilliant idea that, for all we know, is totally wrong. Number 3, the universe follows the geometry of a soccer ball. What is the overall shape of the universe? Einstein's theory of general relativity tells us that space-time can be curved by mass and energy. On a cosmic scale, there are 3 basic possibilities for the geometry of the universe. It could be flat like a sheet of paper in which parallel lines stay parallel forever. It could be open with a negative curvature, like a saddle in which parallel lines diverge. Or it could be closed with a positive curvature, like the surface of a sphere in which parallel lines eventually meet. A closed universe would be finite in size, but without any boundary. If you traveled in a straight line for long enough, you would end up back where you started. For years, cosmologists have been trying to measure this curvature. The best evidence from the cosmic microwave background suggests the universe is extremely close to being perfectly flat. But flat doesn't necessarily mean simple. In the early 2000s, a team of scientists analyzed data from the MAP satellite, which mapped the CMB with unprecedented precision. They noticed something strange. The temperature fluctuations on the very largest scales were weaker than the standard model of cosmology predicted. It was as if there was a limit to the size of cosmic structures. One radical explanation for this was that the universe is not infinite and flat, but finite and shaped like a dodecahedron, a 12-sided object with pentagonal faces like a soccer ball. This is known as the Poincare dodecahedral space model. In this model, the universe is finite. If you travel out in any direction, you will eventually wrap around and re-enter the universe from the opposite side. The universe is like a hall of mirrors. The missing large-scale fluctuations were explained by the fact that the universe simply wasn't big enough to support waves of that size. The universe has a fundamental finite size, and we were seeing its effects. The dodecahedral universe was a brilliant and specific proposal. It made a testable prediction. If the universe were shaped like this, then when we look out at the cosmic microwave background, we should see matching patterns on opposite sides of the sky. The light from the early universe would have had time to wrap around the finite cosmos and appear in multiple locations. Specifically, there should be pairs of matching circles in the CMB temperature map, corresponding to the points where our line of sight crosses through the faces of the dodecahedron. For a few years, this was a hot topic in cosmology. Scientists combed through the map data, searching for these telltale matched circles. Some initial analyses claimed to have found tantalizing hints of such a pattern. It was a thrilling possibility. It would have meant that we had discovered the true size and shape of the entire cosmos. However, after more rigorous and extensive analysis of the WAP data, and later the much more precise data from the Planck satellite, these hints evaporate. The searches for matched circles came up empty. The statistical evidence for a dodecahedral topology was found to be insignificant. The strange lack of power on large scales is still a puzzle, often referred to as a cosmic anomaly, but the dodecahedral universe is no longer considered a likely solution. The simplest explanation, consistent with all the best data we have, is that the universe is either infinite and flat, or so vast that the piece we can observe is indistinguishable from flat. The universe does not appear to have the neat and tidy shape of a soccer ball. It was a beautiful, mathematically elegant idea that was directly tested against observation and found to be wanting. It was a perfect example of the scientific process at work, but the result was that this particular genius idea was wrong. Number 2, the universe has no beginning and no end. The Big Bang Theory posits a definite beginning for our universe, an origin in time from a hot, dense state. For many decades, this idea had a major scientific and philosophical rival, the steady-state theory. Proposed in 1948 by three British-based scientists, Herman Bondi, Thomas Gold, and Fred Hoyle, the steady-state model offered a completely different vision of the cosmos. It was based on an idea called the perfect cosmological principle. The standard cosmological principle states that the universe is the same everywhere, homogeneous and isotropic. The perfect version added another condition that the universe is also the same at all times. In this view, the universe has no beginning and no end. It has always looked, on a large scale, more or less as it does now, and it always will. This was a powerful and elegant idea, but it had to contend with one major observation: the universe is expanding. Hubble had shown that, galaxies are moving away from each other. If the universe is expanding, shouldn't its density decrease over time? This is where the most radical part of the steady-state theory came in. To keep the density constant in an expanding universe, Bondi, Gold, and Hoyle proposed that new matter is continuously being created out of nothing everywhere in space. The rate of creation would be incredibly slow, about 1 hydrogen atom per cubic meter every few billion years, far too slow to be detected directly. But over cosmic scales, it would be just enough to form new stars and new galaxies to fill the gaps left by the expansion. New galaxies would form to replace the old ones that had moved away, keeping the overall picture eternally the same. Fred Hoyle, a brilliant astrophysicist, was the theory's most vocal and public champion. He disliked the Big Bang model, which he considered unscientific and akin to a religious creation story. In a 1949 BBC radio broadcast, he mockingly referred to the rival theory as "this Big Bang idea," a name that ironically stuck. For about 2 decades, the steady-state theory was a serious competitor to the Big Bang. It had a strong philosophical appeal for many scientists. It avoided the messy, singular beginning that the Big Bang required. The universe simply was, eternal and unchanging. The theory also made clear, testable predictions. One prediction was that the universe should look the same everywhere, regardless of distance. Since looking far away is also looking back in time, this meant that the ancient, distant universe should contain the same mix of young and old galaxies as the nearby modern universe. This prediction is what ultimately led to the theory's demise. In the late 1950s and early 1960s, radio astronomers began to survey the sky. They found that there were far more faint, distant radio sources later identified as quasars and active galaxies than the steady-state theory predicted. This suggested that the universe was different in the past, that it had evolved over time. The final fatal blow came in 1964. 2 American radio astronomers, Arno Penzias and Robert Wilson, were working with a sensitive horn antenna at Bell Labs. They were trying to eliminate a persistent, faint background noise, a hiss that was coming from all directions in the sky. They couldn't get rid of it. At the same time, physicists at nearby Princeton University, led by Robert Dicke, had predicted that if the universe had begun in a hot Big Bang, the leftover heat from that initial fireball should still be detectable today as a faint, cold microwave radiation filling all of space. When the 2 groups learned of each other's work, they realized that Penzias and Wilson had accidentally discovered the afterglow of the Big Bang. This cosmic microwave background CMB radiation was a direct prediction of the Big Bang model. The steady-state theory had no natural explanation for it. It was the fossil light from a hot, early phase of the universe that, according to the steady-state model, never existed. The discovery of the CMB was definitive proof that the universe has changed, that it was hotter and denser in the past. The universe is not in a steady state. It had a beginning. Fred Hoyle, to his credit, went on to do groundbreaking work on how elements are forged in stars, but he never accepted the Big Bang, continuing to propose modified versions of his theory until his death. Number 1. The Earth is a flat disk floating in an endless ocean. Before the Greeks understood the Earth was a sphere, the earliest attempts at a rational, non-mythological cosmology came from the Ionian city of Miletus. Around 600 BC, the philosopher Thales proposed that the fundamental principle of all things was water. He imagined the Earth as a flat disk floating on a cosmic ocean like a log in a pond. This was one of the first known attempts to explain the world without resorting to gods and myths. It was a naturalistic explanation. Earthquakes, for example, were not caused by an angry Poseidon, but by the rocking of the Earth on the water's surface. It was a simple, intuitive model based on the world he saw around him. The sea stretched to the horizon, and water seemed to be essential to all life. A generation later, another Milesian philosopher, Anaximander, took a huge conceptual leap forward. He agreed that the Earth was the center of the cosmos, but he rejected the idea that it was floating on water. He asked a brilliant question: what is holding up the water, and what is holding up that? To avoid an infinite regress, he proposed something truly radical. The Earth, he said, is a flat-topped cylinder, like a drum or a column stone. It is held in place by nothing. It simply hangs stationary in the center of the cosmos because it is equidistant from all other things. It has no reason to fall in any particular direction, so it stays put. This was a profound insight, the first known argument for a principle of sufficient reason in cosmology. It replaced a physical support water with a conceptual symmetrical one. Anaximander also imagined the sun, moon, and stars not as objects, but as holes in rotating, opaque wheels or rings that encircled the Earth. Through these holes, we see a great cosmic fire that is hidden behind the rings. A solar eclipse was explained as the temporary blockage of the sun's hole. These early models were genius for their time. They represented the birth of science, the move from what is the story to what is the mechanism. They were based on reason and observation, however limited. The idea of a flat Earth was not a foolish superstition. It was a rational first guess based on everyday experience. The world looks flat. The idea that you could sail too far and fall off the edge was a much later invention, a caricature of medieval thought. Most educated people from the time of the ancient Greeks onward knew the Earth was a sphere. The evidence was clear: the curved shadow of the Earth on the moon during a lunar eclipse, the way ships disappear hull first over the horizon, and the way the visible stars change as you travel north or south. The flat Earth and cosmic cylinder models were wrong, but they were wrong in the best possible way. They were bold, rational attempts to build a model of the world from first principles. They were disproven not by faith or dogma, but by better observations and more sophisticated reasoning from within the same scientific tradition they helped to create. Anaximander's Earth, hanging unsupported in the center of a symmetrical cosmos, was a stepping stone to the Aristotelian idea of a spherical Earth at the center. Fowles's idea of a single, fundamental substance was the beginning of the search for the basic building blocks of matter. These first cosmologies were the crucial first drafts of our understanding of the universe. They were the brilliant, necessary, and totally wrong ideas that got the whole process started.